Hey tech learners, how are you? In last presentation, we discussed about stacks and queues. Today is a new topic, introduction to trees. We all know that in day one of the class, I have told you trees are a non-linear data structure. So, in today introduction is about trees. Introduction to trees and a data structure. A tree is a widely used abstract data type that stimulates a hierarchical tree structure with a root value and subtrees of children with a parent node represented as a set of linked nodes. So, in the key terms or key terminologies here we use in the tree is node, root, parent, child, leaf, edge, subtrees, head, height, and depth. And further, I'll tell you about what is all that. So mainly we'll tell about first root. Root is nothing but a parent. A node that has branches, one or more child nodes is called root. So parent and child nodes directly that are connected. A node that has branches, one or more child nodes. Child is nothing but a child that descends from another parent, another node. And leaf node. A node that has no children is called leaf node, and another one leaf edge. The connection between one node and another is called edge. Subtree. A tree transformed by a node that descends is called a subtree. First, what is a node? A node is nothing but each element in a tree is called a node. The height and depth also we calculate here. The number of edges on the longest path of the node is called height, and the depth is the number of edges from a root to node is called depth. So there are many types in trees. We have general tree, binary search tree, balanced tree, heap tree, and some more are completely binary tree, full binary tree, AVL tree, B tree, and prefix tree. These are some more optional ones. So first we generally discuss about a general tree. What is a tree? Nodes can have number of children. It means one node can have many number of children as it means. That is called a general tree. It's a general tree structure. What is a binary tree? Like each node have at most only two children. It means a node contains two children, left children and right children. Then it is called a binary tree. Binary search tree. A binary search tree where the left children is less than the parent and the right children is greater is called a binary search tree. See, you can see here left is less than parent, less than right. So if it is in the form of this, then it is called a binary search tree. Next, balanced tree, height difference. A tree where the height difference between the left and right subtree is minimal, then it is called a balanced tree. I'll tell you furtherly, I'll discuss it about. Next, a heap, a complete binary tree satisfying the heap property. We all know heap. Heap is in next class like in next slide there is a complete introduction about the heap. Next, what are binary tree traversals? We all know that traversal is nothing but visiting all nodes. So in traversal we have three types: in order, pre-order, post-order. Like in order, we'll traverse all the left nodes first, then root node, then right side nodes. Then it is called in order. Pre-order means root. We'll visit root first, then left side nodes, then right side nodes. Post order means first we'll see left, right, root. This is called traversal techniques. We have three types. Mainly we use in order, left, node, and right. Node is nothing but root, parent, anything. So this is called traversal techniques. See, here is an example. Now see, A is called a root node. We have it is a binary tree because it have two children. So guys, see here, there is a binary tree here. A is a parent node and B, C are the child nodes. B have another two child nodes D and E. C have only one child node F. So in order, what I told you about what is in order. In order means left root, I mean node right. In the order visiting like in left node right. So first what are the left nodes? See, the leftmost node is D, then B, then we have another left node E here. Next, already B is traversed, so it will go like this. Then it goes to A because left node all completed. It goes to root node. It is A. Then it will traverse the right node. So C. First, the right node is C. After F. I hope you understand. Next, in pre-order we have first node, next left, next right. So what is the node? A. Next left side what is there? B. After that D. After that E. And next right we have C and F. Next post order we have left, right and root. First what is in left side? We have D, we have E, then B, then right. We have a rightmost F. After next that C, next that root node A. Like that the traversal will be. So a tree have some operations like insertion, deletion, traversal, searching, height and depth measurement. Insertion is nothing but adding a new node to the tree. It may be a leaf node. We can add near a leaf node or at, in the middle of the nodes. We can add deletion like removing a node from a tree. Searching, finding a node with a specific value. Traversal like visiting all the nodes. Height and depth measure balance and efficiency. Binary search tree operations. In binary search tree, like I already told you what is a binary search tree. Left less than parent less than right. The tree will be like that. So we have some operations in binary search tree. This is very very important. So we have operations like same insert, delete. In delete we have three operations may done. Next one is search operation. First insert. Insert like placing a node based on the value. I'll tell you all that how insertions and deletion happen. Next one is no deletion. Deletion is like no child. If there is no child nodes, we can remove directly. If there is one child node, we'll replace the child node and we'll delete that. In two child node, we'll replace with in order successor or predecessor. And search operation is also done in binary search tree. Applications of trees, hierarchical data, modeling example file systems and organization charts. We can also do databases and indexing example B trees and B plus trees. Next, networking, spanning trees, expression parsing, syntax trees, AI decision trees, and compilers extracts syntax trees. Advantages of trees. In natural hierarchical representation, efficient for search operations, widely used in database GUIs. GUI is nothing but graphical user interface and algorithms. Summary. These are essential and non-linear data structures. A binary tree, especially BST, are widely used, and a traversal allows structure node access. Trees supported diverse operations and applications. Okay guys, I'll tell you what is a binary search tree and operations here. Uh, so let's imagine a tree. So I have a root node of 7, let's think. It have two child nodes. In binary search tree, the root node must be minimum here. Okay, I'll tell you with here example only. We have let's take in order thing D B E A C, and I'll keep the root node as first. So D is there here. It have two child nodes. So B and E. B is less than this, so I'll write left side. And E is greater than this, then I'll write here. Next A. A, D, it is less than b, so I'll write left side. Next one is c, it is less than and it is greater than b, so I'll write here. Next, what is the f? So it is a binary search tree. So what are the operations we have in a binary search tree? See, insert, delete and search operations we have. So like this we insert in a binary tree. Insertion is very simple, like the first node, the first element which is there, we keep that in a root node. It is a root node, and next elements will keep, if it is less then we'll keep left side of this, or if it is greater than the root node we'll keep it right side. Searching is also same. If you want to search an element e, suppose, so first we'll check in the root node. The root node is D. So D is less than E. So it might be in the root right side of the tree. Compulsory. It is a binary search tree, no? So we'll check in the right node only. So the right side of E. We can see E here. If you want to search A, suppose, then first we'll check in root node. In root node we have D, so D is less than A. We'll check left side nodes. We have left side B, so B is less than A, so it must be left side of A, so we find A there. Like this we insert and we search, and deletion is done like, if you want to delete F is a leaf node. This is called leaf nodes, which does not have any children. I have told you before only. What is a node? A leaf node. A node with no children is called a leaf node. So these are called leaf nodes. If you want to delete a leaf node, it is very simple. We can just delete this. No need of replacement. If you want to delete a nodes like child nodes, parent nodes, if you want to delete, if it have only one child, like if you want to delete E, you have to replace the leaf node with the child node. Like you have to replace E with the F. Then what will happen? So then F becomes here and E becomes here, and it becomes a leaf node. So we'll replace here and we'll remove this. Just it is as simple as, so these are the deletion techniques in binary search tree. So another what we have, applications, advantages. Okay, this is called a binary search tree, and the operations like this it will be. So next I'll tell you about what are we seen about binary search tree. Now next one, AVL tree and B trees. So guys, we have seen about binary search tree, and here is an overview on binary search tree. I'll tell you again. It is a tree. First, what is a tree? Tree is a hierarchical data structure used for searching, sorting databases and file systems. In this PPT, like in this slideshow, I'll tell you about again what is a binary search tree. Just I'll give you a brief intro again, and a AVL tree and a B tree. So we have already seen what is a binary search tree. It we have to only remember what is a binary search tree means. Left subtree less than root less than right subtree. Here no duplicate values will be here. So next, BST operations we have seen insertion, deletion, searching, traversal. In traversal we have in order, pre-order and post-order. In time complexities is nothing but how much time it will take to complete an operation is called time complexity. We have another terminology called space complexity. These both are very important. Space complexity is nothing but how much space it requires to complete the operation. So, in future classes, we'll learn more about these time complexities and space complexities. And now we see for average case and worst case time complexities. It is big O of log n and big O of n. So we have seen BST applications. It is used for implementing dictionary sites, it symbol tables in compilers, autocomplete features, and binary search logic. And the BST advantages are easy to implement, efficient in searching in balanced trees, simplified recursive operations. So next, what is an AVL tree? First, what is AVL? AVL is nothing but Adelson, Veleski and Landis. It is named after its inventors. An AVL tree is a type of a self-balancing tree. A binary. It is also a binary search tree where the difference in heights of the left and right subtrees. It is called balancing factor of any node. It must be at most of 1. It means it must be -1 or 0 or 1. It is a balancing binary search tree. Like we have to check balance factor for each node after if we done an operation, we have to do this balance factor. Balance factor is means height of left side minus height of right subtree. It is called balance factor. For any node, we use this. So balance factor, it is very important in AVL tree. The formula is height of left subtree minus height of right subtree. So it must be -1 or 0 or 1. So we have AVL tree operations, we have insertion and deletion. So it requires some rotations. Here, if the balance factor is not between -1, 0 or 1, then we do some rotations like left rotation, right rotation, left right rotation or right left rotation. LL, RL, RR, LR. So when do we do these rotations means like first we do if we do if we perform an any insertion operation, like insertion is done in like normal BST tree, how we insert same like that, because it is also a binary search tree. After insertion we have to update the height and we have to check the balance factor here. So if it is an unbalance, we perform the rotations based on the height difference where it is, we do that. Same like deletion also, we delete like a regular binary search tree. After deletion, we update heights and we check the balance, perform rotations if any node becomes unbalanced, and rebalancing may be needed at multiple levels on the path back to the root. So time complexities of AVL tree, we have big O of log n here for search, insert and delete operation. We'll see AVL applications later. I'll show you how to insert and how to check the balance. For suppose if we take a tree binary search, like same numbers will take 5, 3, 7, 10, 2, 3. 3 is already there. 5, 3, 7, 10, 15 we take. So first we construct, like we insert the tree first. How we insert a tree? First we'll take the root. 5 is inserted. Next, it is balanced because left node we don't have anything, right node we don't have anything, so its balance factor is 0. Next, we how to insert 3. 3 is less than 5, so we'll insert left side of this 3. So now check the balance factor. How to check the balance factor? So checking balance factor, like first from leaf node we have to check. Left side it have doesn't have anything, and right side also it doesn't have anything, so it have 0. Here 1 minus 0. So 1 minus 0 is 1. So it is balanced. Both the things is balanced. Next we insert 7. 7 is bigger number, so we'll insert right side. Now same again, we check the balance. Here 0, here 0, 1 minus 1 0. So it is balanced. Next we have to insert 10. It is bigger than 5, it is bigger than 7, so we insert right side 10. Now see the check the balance. Here 0, here 0, here nothing is there left side, so 0 minus 1, it is minus 1. Here 1 minus 2, 1 minus 2 is nothing but minus 1. So all them are balanced. We have next 2 we have to insert. It is less than 3, so we'll insert here. Now see 0 here, 0 again here, 1 minus 0, like left minus right we have to see. 1 minus 0. Shabba. So 1 minus 0. 1 minus 0 is nothing but 1. Balance factor is 1. Here 0, it have minus 1 here because 0 minus 1. We have 2, 2 minus 2, 0. So all are balanced. Next we have to insert 15. So insertion of 15 will be 10 right. Now check the balance. Leaf nodes always have 0. So you just remember again 1 minus 0, it have 1. Dekho here 0 minus 1, it will be minus 1. Here 0 minus 2, we got minus 2 here, so it is unbalanced. So we have to do rotation. See how we have 4 types of rotation, like left rotation, right rotation, left right, right left. What rotation we have to perform is the main important thing we have to do here. So where it is unbalanced, because it is unbalanced at a right node, so we'll perform if left rotation here. If it is unbalanced in right side, we performs left rotation. We make this as left. I'll show you. So how it is there? 7, 7 to right, 10, 10 right, 15 right. So how we'll do means we keep 10 in middle, and we'll write 7 left and 15 right, like we just move this one left, so it is called as left rotation. So here 10, 7, here 15. So now check the balance. 0, 0, 1 minus 1, 0. Here 1 only. Here if there is many nodes like this, then we have to check the longest chain. Here it have 2 nodes, here 2 nodes, so anything is no problem. 2 minus 2 0, so it is balanced. Like that we have to check. Simple, it is very simple. Just we have to check the balance. So if the balance like it is unbalanced this side, we have to make left rotation. If it is balanced, unbalanced right, like unbalanced left, we have to make right rotation. It is the only thing we have. Very much easy. Time complexities we have seen. So AVL application. Why we have to use these AVL trees? It because it maintains balance. We need balance, right? It guarantees height faster and more predictable than unbalanced BSTs. In binary search tree, we don't have this balance, so we need to use this AVL trees. AVL tree applications are database and file systems in memory sorting and also routing tables in networks. AVL advantages: guarantees a big O of login operations, auto balancing avoids skew trees, efficient for searching heavy application. So next we are going to learn about B trees. So B tree is also a self-balancing search tree designed for systems that reads and writes a large block of data such as databases and file systems. Unlike binary search trees, B tree can have more than two children, making them a multi-way trees. So in B trees, it doesn't have only two child nodes; it have more than two child nodes. So that is the only difference between a B tree and a binary search tree. So nodes can have multiple keys and children's. All leaves are at the same level. It is the main feature. So there are some key features of binary search tree. It is balanced. The height remains balanced automatically. It is sorted. Keys are in sorted order. Multiple keys per node. Each node contains multiple keys and children. Efficient disk access minimizes the disk read by maximizing the data per node. High fanout reduces tree height and improves the performance. So these are some important key features, and B tree have three operations like searching, insertion and delete. Insertion, I'll show you how the operations performs. First you have to know about the properties of a B tree. Every in B tree, every node has at most 2t-1 keys. Every internal node except the root has at least t-1 keys. Root has at least one key. It or can be a leaf. All leaves appears at the same level. Keys are always sorted within the node. So the structure of a B tree node contains up to 2t-1 keys, where t is the minimum degree and 2t to 2t children. All leaves are should be at same level. So the time complexity of B tree is big of log n. So how insertion operation is done? So insertion is done like insert the key in approximate leaf node in sorted order. If the node becomes full, like more than 2t-1 keys, then we have to split it. Splitting is done like median key moves up to the parent and split the node into two separate nodes. It may cause recursive splits up to the root. Same thing, deletion also more complex than insertion. Maintains T properties by merging or borrowing keys from siblings if necessary. Replace the keys with the predecessor or successor if deleted from the internal nodes. Ensure nodes do not fall between two t-1 keys. The search operation is similar to binary search but across all the keys in a node. Recursively descend to the approximate child node. So I'll tell you the applications before I'll start the operations. B-tree applications are database, efficient indexing and storage, example MySQL, file systems, file system for block oriented storages like NTFS or HFS, operating systems for disk based operations, block storage and disk based systems. So some B-tree advantages are optimized for disk I/O, supports large data blocks and balanced with minimum rebalancing. Comparison table between BST, AVL and B-tree. BST is not balanced but AVL and B-tree are balanced. Keynotes like keys, it have only one. B-tree have multiple keys. Best for RAM, real-time, disk, insert time is big O in here, and both AVL B have big O of login. So I'll tell you how operations done. So guys, we'll see B-tree insertion. Where it is place. Okay, I'll do here. So if we have to insert keys here, I have already told you before, it can have multiple keys. Like if here we have a terminology called order. If it is in the order 4, let us think the B tree have as an order 4. It is our wish, we can take any image order. It means it keys must be of order -1, like 4 minus 1 keys should be there. It means it have to have 3 keys and maximum of 4 children. So this is the main thing in B tree. So let us assume that we have to insert values 10, 20, 7, 11, 5, 15, 30. Okay, let us take these values. First we insert 10. 10 will be inserted. Next 20. It must be in a sorted order, I have already told you. So 20 will be here. Next 7. 7 will be in front of 10. 7, 10, 20. These are called keys. Okay na? Next 11. 11 we have to insert between 10 and 20. Where it is gone? So between here we have to insert. But we have order 4, right? So there must be a maximum of only 3 keys. So here it goes to split, like the 11 will go up. So 11 is divided and it have 7 here and 10 also less than, so it will be left. And 20 will be right because it is greater number. So like this it is inserted. Next 5 will be inserted here. Next 15 will be inserted here. Next 30 will be inserted here. If there is another number, like if we have 2 also here, then we have to insert here, but there is only maximum. No, so we can't able to insert here, then it goes splitting. 2 will be inserted here and 7 will go up, like 7 won't be there here. This 11 is going to 7 will be here and 11 will be here. Mm, what are the values here? 2, 5 and 10, right? Now 7, like see, it is not in a binary search tree because 10 is greater than 7, so here 10 will be deleted. 2, 5 will be here only, 10 will be middle. Like this the binary tree is constructed. I hope guys you understand this. It is somewhat confusing, but it is very easy. Once you just practice all these trees, binary search tree, AVL tree and B tree, these are very important topics. uh, so I'll come to an conclusion that binary search tree is simple but it is unbalanced. AVL is fast, balanced in memory, and B tree is this efficient, scalable. It is chosen based on your needs. Thank you for listening my class. If you have any questions, please comment me down, or you can contact me through the channel. Thank you guys.